This video is the second video in a two-part series on neural networks. Unless you're already familiar on gradient descent, I highly recommend you go watch the first video. Now that we've learned the basics of curve fitting, let's finally get into neural networks. Neural networks, just like lines, are functions. They take in a list of numbers as the input and then output a list of numbers. Neural networks are composed of neurons. Each neuron is actually just a single number. Neurons are arranged in columns called layers. Each neuron in each layer is connected to every other neuron in the next layer. When we say two neurons are connected, we mean they are connected by a weight. Here 1.25 is the weight, so the left neuron's value is multiplied by 1.25 before getting added to the right neuron's value. After all the values from the previous layer are multiplied by their respective weights, the bias is added. This is another parameter that offsets the value. We start from the input layer, where the neuron values are set to the list of the inputs. Then we work left from right, working out each layer until we get to the output, where the output layer's values are transferred to the output. The layers in between are called hidden layers. So the order is input, hidden layers, output. Right now, our neural network function looks something like this. However, if simplified, it will only ever be a line, since they are only linear terms. We need to introduce some things that are not just simple multiplication and subtraction. This is the ReLU function. If x is less than 0, we clamp it to 0. The ReLU function is called an activation function. It makes the output non-linear through acting as a sort of a decision gate. It's the most common activation function because it's the easiest to calculate. Here are some examples of other activation functions. This decision gate is applied after each neuron's value is calculated, so after the bias. This also makes the neural network a universal function approximator. It can fit through any function given enough neurons. If you think about it, the left part of a ReLU is 0, so if you add another ReLU, only the right part matters. This is why you can just piece together a function using just ReLU segments. But how do you train a neural network? Well, using gradient descent, of course. We adjust each bias and weight to make the output loss as small as possible. We want to find the derivative, how tweaking each bias and weight affects the output loss. Let's first go over the steps for how to calculate a layer's value again. First, the last layer's values are passed in. Each neuron in the last layer is multiplied by its respective weights for each neuron in the next layer. Then the biases are added to each neuron in the next layer. Finally, the neurons in the next layer are passed through the activation function, usually a ReLU. This is a three-step process where in each step the input is the output of the last step. Sounds familiar? Yes, the calculations can be split into three separate functions. Now we can apply these equations that we learned about earlier, the chain rule. We can actually split the first function into two new sequential functions and then apply the chain rule on that as well, so 3 functions. We can generalize this for any number of sequential steps. To get the derivative of the end result with respect to the input at the start, we just multiply the derivatives of the individual functions. With this rule in mind, we can easily find the derivatives with respect to the biases and the weights. So for a sequence of functions, we first run it to find the inputs at each step. Remember that the derivative is a function of the input. We start going back from the output and accumulate the derivatives in between and finding out all the derivatives of the parameters. First, let's find the derivative of the ReLU function with respect to the weighted input. The right part of the function is just y equals x, the simplest of lines, so the derivative is 1 for x greater than 0. The left part is clamped to 0, so the derivative is 0. It doesn't change at all. But what about x equals 0? The derivative from the right is 1. The derivative from the left is 0. It's a sharp point, so the derivative is actually undefined here. We can just set it to any number we want. So we start with the derivative of the ReLU function with respect to its inputs. Adding the bias doesn't do anything, so we can just copy this derivative to the bias for gradient descent. Now the weights. The weights are scaled by the input, so the derivative of the weights is just the input multiplied by the right part. Now what about the derivatives passed on to the inputs? Since the derivative of wx is w, we simply multiply each weight by the derivative on the right. Now we found a way to propagate derivatives from the end of a layer to the start. Using this method, we can find all the derivatives in the layers. But remember, these are the derivatives of the loss function. What is the derivative of the loss function with respect to the neural network's outputs? A loss function can be written as this. For each output neuron or number in the output list, for the data points up to n numbered I, the difference between the data point's actual value yi and the neural network's predicted value y hat I is taken and squared. Then all of these squared values are added together. Remember that this happens for each number in the output list. Now we add another sum. We sum over this for all the numbers in the output list. This is so we can make one final number, the loss. Now remember that the derivative of a sum is just the sum of the individual derivatives, because their effects are added together. Now, as we did with the line thing last video, we just find the derivative of this part like this. Now, first ignore the m part. We can just repeat this process for every single data point. Remember that we found the derivative with respect to y hat ij, which is the neural network's output. Now we can copy these derivatives to each neuron in the output layer. Now remember that the derivative needs the actual value of the inputs. This is why we run the neural network first, storing the value at each intermediate step. Also remember that we're trying to find the loss derivative with respect to each weight and bias for gradient descent, using the chain rule, which requires it to multiply every derivatives in between that and the actual loss function. This is why we start backwards from the output layer, accumulating all the derivatives in between by multiplying. We go backwards and find the derivatives for each weight and bias, repeating for each of the data points. In gradient descent, we multiply each of the gradients by a small number called a learning rate. This is to prevent the point on the loss function from taking two big steps. This is called backpropagation. We propagate the derivatives backwards. Now, what are the applications of neural networks in real life? You might train a neural network to identify if an image is an image of a dog or an image of a cat. Now, as you may know, images are represented using pixels. Pixels are colors represented by three numbers, R, G, B, representing how much red, green, and blue is in that pixel. The image is flattened out into a list of RGB values, then fed into the neural network. The neural network returns two weights which represent the probabilities of one image being a dog or a cat. Now, ChatGPT. Sentences are split up into words or syllables called tokens. Tokens are small units that commonly appear in sentences. Each token is assigned a unique number or ID. The list of tokens are fed into a function that returns a list of probabilities for the next token. Then the next token is chosen according to the list of probabilities, and the process repeats. Yeah, ChatGPT is just a glorified version of autocorrect. By the way, this function is not just a simple neural network. It's composed of many parts. First, the tokens are encoded into lists of numbers that represent meaning using context from other tokens. Then they're passed into multiple layers of neural networks and cross-attention mechanisms, which I'm not going to explain today.